Hey everybody, so this is the last video going over section 2.3. Hopefully I can get you these two problems, or get you this one problem, get these two slides, and then be done, and you guys can have the rest of the period as your work day over section 2.3, and then the homework is going to be due on Monday. All right, so the last thing that I need to talk about here is this thing called the squeeze theorem. Now before we get to the squeeze theorem, we have to have this theorem that kind of leads us into it. And again, if you ever want to, over the weekend, if you want to do some light reading, their proofs can be found in Appendix F of the book. So, if you're struggling with things to do over the weekend, you can always read your calculus book and all the proofs in the back. All right. So this theorem says that if f of x is less than or equal to g of x, so I've got two functions, one smaller than the other. If f of x is less than or equal to g of x, where x is near a, and the limits that exist, then the limit as f of x goes to a also has to be less than or equal to the limit as x approaches a of f of x and then s to g of x. Let me read that one more time. If I've got two functions, one vertically, and again, because these are the outputs, one vertically underneath the other. When x is near a, and this is the whole idea of being near and not at, and the limits both exist, then the limit as x approaches a of f of x also has to be vertically underneath the limit as x approaches a of g of x. So if the functions are underneath, then the limit is underneath. Now, conversely, I could just go backwards with that too. I could say greater than or equal to if I really wanted to. Now, what does that lead us into? That leads us into this thing called the squeeze theorem. It says that if you have two functions, f of x and h of x, and they're on either side of this g of x, okay? And what do I mean on either side? I mean one's underneath it, f of x is under, and h of x is over, okay? If you've got one function underneath it and another function over top of it, and I know that their limits both converge to the same thing, like look, the limit as x approaches a of f of x is L, the limit as x approaches a of h of x is L. So I know the limit here is L, and the limit here is L as x approaches a. If you know all of these things to be true, f of x is under, h of x is over, and they both are converging to the same limit at a, then you therefore know that if these are L, this has to be L as well. The limit as x approaches a of g of x also has to be L. Basically, what you're going to do is you're going to create kind of almost like a boundary. You've got this function g of x, and you're almost going to create a boundary. You're going to create a lower boundary and then an upper boundary, and then say, okay, if I apply the limit to the under, and then I apply the limit to the over, what I can do is say if the limit comes out to be L for the under and the over, well, that must mean that this must be the case where it's equal to. So it's got to be L as well at G. Let me show you what it looks like. A couple names for it. It's called the squeeze theorem. I think I joked about it. My calc professor had that heavy accent, called it the Sandvich theorem with a V in it. Sandvich, V-I-C-H. I've never really heard it called the pinching theorem. I don't know. But this is what it looks like in terms of the graph. You've got f of x under. This is the under. You've got g of x middle. You got h of x over. And we're saying if the limit as x approaches a of the under equals L, and the limit as x approaches a of the over equals L, then the limit as x approaches a of the middle must equal L as well. Okay, that's the sandwich theorem. Now, how can we apply that? All right, so take a look at this function here. Find the limit such that x is going to 0 of x squared times the sine of 1 over x. Now, can I just do direct substitution here? You may be questioning it because we haven't done any trigonometric yet. But even if I wanted to do the trigonometric, could I plug in? No. So that's a bummer. I can't do direct substitution. So maybe I can use this sandwich theorem. First, go with me here. If I wanted to find the sine of 1 over x, Look for something that's bounded, like the sine. Think about the range of sine. Along the unit circle, no matter what I plug into sine, it's going to be at most +1 and at least -1, right? Because of the y values, the smallest it could possibly ever get is -1, and the biggest it could possibly ever get is +1, no matter what I plug into sine, right? It doesn't matter what I plug into sine. 1 over x, 1 over doesn't matter. The outputs are always ever going to be -1 to +1. So I can say this, it's never going to be underneath -1. It's never going to be over +1. Okay. Well, I have this part in there now that's bounded, but I don't have anything to do with an x squared yet. So let's just multiply by x squared to this whole thing and see what happens. -x squared sine, oops, I forgot my I, sine of 1 over x, 1x squared. Okay, so right now this is the premise of the squeeze theorem. I've got some function f, the under, I've got some function h, the over, and I've got this middle function g. It says that if you apply the limit to all of these things, x goes to 0, say, of x squared, -x squared, and you evaluate that, and then you apply the limit as x approaches 0 of +x squared. And if you know those to go to the same thing, then that middle function must also go to that thing. The nice thing here is, look, can I do direct substitution now? Yes, I can. This is 0. It would say -0 squared, but 0. This is also 0. So what I'm saying here is the limit as x goes to 0 of -x squared can be less than or equal to the limit as x goes to 0 of x squared sine 1 over x is less than or equal to the limit as x goes to 0 of +x squared. And we know this is equivalent to 0, and this is equivalent to 0 because we just showed that. And look, it squeezed it in. It's saying that at that moment, it's in between those things. And if it's in between those things, well, what's the only thing in between less than or equal to and still greater than or equal to 0? 0. That's it. So we know this full limit is equal to 0. Okay, so that's how you can apply the sandwich theorem or the squeeze theorem. You can show some sort of boundary. You got to think about your original function and say, okay, is there any sort of boundary that I can use? Usually it's going to be like trigonometric or something like that. And then apply the piece that's unbounded to all parts, left side, far left side, far right side, and middle. Try to get the original function, x squared sine 1 over x here. Then apply the limit to the whole thing. Find the limit as this. Find the limit of the left side. Find the limit of the right side for both of them. And then you can say that if they converge to the same number, then this middle function also must converge to that same number. That's the squeeze theorem. Okay. All right, enough of me talking. We are not going to talk about that last slide. So we are good. So hopefully we get a good amount of time to work on our homework. Hopefully. Oh, if you need anything, folks, I will be around the second half of the day. I've taking my daughter to the doctor in the morning. So I should be around during the second half of the day. I'm only taking off a half day. So stop by and say hi. Have a good weekend.